Okay, I hope that you can hear me right now. So first of all, I wanted to thank you for your understanding about the lecture today. As I mentioned in my email, I was asked to participate in a program review, and there was a last minute change of time. And unfortunately, it conflicted with our lecture. So I decided to record my lecture, and is going to become available to you at 1:35, the normal time we start our class, and it's going to end around 2:25. And at the end of the lecture, you will be also able to access the quiz, and either you can spend time to solve it then, or you can try to solve it anytime between tomorrow at 2:30 approximately, and the time we come back in class on Monday. And the material for the quiz is going to be whatever we covered during this past week. Also, I will be available for office hours today. I will be done with my presentation by 2:40, and I should be, in fact, able to connect for the 3 p.m. office hours Zoom meeting we have. And so if you have any questions about the lecture itself, any questions about the homework or anything else, you can join me during office hours. In addition, this weekend, I'm going to also release the next assignment for the project, which is the design of your filters. And you're going to have 2 weeks to complete that. You will have more than one, some of you will have more than one filters to design, and we have now covered enough material, not everything that the book has, but enough material to be able to complete those designs. And with the material we'll cover today, and maybe a few minutes of Monday morning, I believe you will have then all of the tools that you need for any type of filter design. However, if some of you feel comfortable or want to use different types of designs, there is a host of designs available, then you will be welcome. In fact, it will be fantastic if instead of the designs we just did in class or the ones that we covered in our lectures, you wish and are able to just do a totally different type of a design for your filter, as long as you verify those designs using MATLAB or Multisim or something else. And so we will talk about this obviously on Monday again, but I just wanted to mention. So with that, I will share my screen. And what we will do is to continue with the designs we discussed yesterday. So, I mean, on Wednesday. I would like, so at this point, to just remind you of where we were. We had developed the low-pass prototype, and from there, we used the low-pass to band-pass transitions or transformations, if you like. And then we moved from the CLC, low-pass prototype, to something more complex that has L1C1 in parallel and in shunt configuration. L2C2 in series and in series configuration, and also L1C1 in parallel and in shunt configuration. And you can observe that this is a symmetric filter. So this parallel configuration is identical with this one. And we got the values for L1, C1, and then L2 and C2. And you can see that the prominent parameter from all of this is L2. But obviously, they're all designed to create an LC type of a filter that has the specs that we have requested. And the specs, so just to remind you, are here for this filter. In fact, let me think right here for this filter. And it does ask for a bandpass at 10 gigahertz resonant frequency, 10% bandwidth, 50 ohm input and output ports, and 20 dBs rejection at 20 gigahertz. And we use the 0.5 dB ripple. And we use the equal ripple or the Chebyshev type, if you like. Okay. Now, we did this, and finally we came to that. And now, before we proceed and ask the question how we are going to implement this one, I wanted to make two observations. First of all, in the low pass to band pass transformation, we went from a series inductance to a series LC, inductor capacitor. And what we find in this transformation is that as we go from just a simple inductor to an LC circuit, then the resonant frequency for this LC circuit is given by the known form of the resonant frequency of a circuit, which is 1 over square root of L prime C prime for our case, obviously, because L prime and C prime are the inductance and the capacitance that we have in our resonant circuit. Also, as part of the low pass to band pass transformation, we had to replace each one of the capacitors with a shunt but parallel configuration of L prime and C prime. And also again here, you observe that the resonant frequency for that L prime C prime circuit is the design frequency for our filter, and it's given by this also formula. And here I have to add primes for both of those. Okay, now before we proceed and try to figure out how are we going to replace all of these elements we have. So we have a parallel L and C, two of those parallel configurations, and then we have one series LC configuration in the middle. We will have to look at some implementations in microstrip form of different types of circuits. So practically, we will look at different types of ideal transmission line types of circuits and how they are implemented in microstrip form. And that is going to help us, as you will see. So let me start with, this is a microstrip, as a matter of fact, so we have it here to remember that a microstrip, the characteristics are the type of the substrate you have, and that's given by ESA bar, and that's the relative dielectric constant. Obviously, the dielectric constant is going to be the relative ESA bar times, or epsilon sub bar times epsilon sub naught. H is the thickness of the substrate. W is the width of the microstrip, and we will assume in all our applications that the skin depth, which means how much the current flows inside the conductor, that's called skin depth, a measure of that, how much the current flows inside the conductor. As a matter of fact, there is a way to identify that, but we will assume that that skin depth is much smaller than the thickness of the metal. And the thickness of the metal, if you remember, is this one. Oops. The thickness of the metal is this one. So, and if we call that T, we assume always the T is much larger than the skin depth. Okay? So delta is skin depth. And for now, in all of these implementations, we'll assume that we have no losses at this point, all right? And you will not see any losses. I don't talk about losses at this point in the metals. So even if I have made that assumption, and we will always stick with that assumption as we will design our circuits for the system, in reality, there is always a loss, but in what we are presenting right now, that loss is not incorporated. Okay. Now we have a section of a transmission line. Z0 is the characteristic impedance, and L, its length. And we would like to find what kind of an equivalent kind of an LC circuit we can consider, because if we have that in mind, then we can go, if we know how you go from a microstrip or a transmission line to an LC, then you can use the reverse and go from the LC or just L or just C back to sections of transmission line. All right, so we are gonna see those equivalent structures. So equivalent circuits is when you take, what do we mean by an equivalent circuit is when you take a realistic circuit, in our case can be a transmission line, a realistic one, and then you represent it with an LC or an RLC if you want to incorporate losses, of an LC for our case without losses circuit. All right, so an equivalent circuit is by definition LC. All right, so how are we going to go about finding an equivalent circuit? First of all, for a section of a transmission line of length L and characteristic impedance Z0. And if you remember, this is just a review. You start with this schematic that we have seen in Poser's book when we did the network parameters. And that tells you that if you know the impedance matrix of this section of line, then you can find an equivalent circuit where you're going to have three elements, and each one of them is given by those Z11 minus Z12 for this element here, Z22 minus Z12 for that, and then Z12. So the most critical thing, therefore, for that particular section of line is to find the Z matrix. How do we find the Z matrix? We start with the impedance matrix, which is already given in the book. That is the impedance matrix for a section of line. I mean, if you look at Poser's book, you will find that. And then from the ABCD matrix, and again from the book, where there is this one page, there is a whole matrix of transformations from every one of the network matrices to any other one. So then you can find your impedance matrix from your ABCD matrix, and finally it gives you this one. All right, the four elements of the impedance matrix. Now we take each one of those, we substitute back here to find those differences and to find Z12. And you will see here the calculations very extensively. We come to the following two cases. First one is we find Z12 and from Z12 we have in fact you see that the expression for Z12 provides an equivalent capacitance here. All right. And this equivalent capacitance is very important to keep in mind, because practically what it tells you is that you can replace this one here with a capacitor. And the value of the capacitor is given by this formula. So that's number one. Now we are going to Z11 minus Z12. In fact, you will see that Z12 and Z21, of course, are the same, but also Z11 and Z22 are the same in this matrix here. You will find that Z11 and Z22 are the same. And of course, Z12 and Z21 are the same. And that implies that we only have to calculate this difference. And then if you do that, you come down to the following expression. It's this one here. All right, now we make an assumption. Let's assume that we are using a small length of line. You see that? If you use a small length of line, in fact, since you may not see it very well, I will remove that. And I will use this one here. A small length of line implies that the product beta L is much smaller than 1. That does not mean many orders of magnitude. It could be just 0.1. All right. Or it could be even 0.4. It's just far from 1. It should not be close to 1. I put the double inequality just to emphasize that it should not be close to 1. I should be definitely below 0.3. Okay. Sometimes you can, in fact, instead of going below 0.3, you can push your limits, but you just need to remember we're talking about small sections. For a small section of line, then, you can simplify. You may not remember that, but I just put it here for your reference, that you can express your sine as a series, that all of these are converging series for small beta L, and then the cosine as well. And if you simplify all of this, finally you come with that relationship. This is what you need to remember. And from this, you get, what you find out is that the difference Z11 minus Z12 in this circuit here, the difference up here, so the difference up here is equivalent to an inductor. So by going back to what we have, so here you can see that, as we said, the Z11 minus Z12 becomes equivalent to an inductor, and this inductor is given by this formula. And we found that Z12 is equivalent to capacitor, and this capacitor is given by this formula, the value of the capacitance. Okay. So having that in mind, what do we find? First of all, we found from the above, then we can take a section of line like this that is short compared to the wavelength, a short line compared to the wavelength. And the equivalent of this line is kind of simple. It's like a symmetric, it's like a T circuit that has two inductors, each one of them equal to L/2, and a shunt capacitor. And then the inductor here is given by this, and the capacitor here is given by that. So both in the inductor and the capacitor are proportional to beta L. Okay, that is very important, obviously, because for a short section of a transmission line, we can find an equivalent circuit, which is an LC. But now we are going to look into some two interesting cases. One is where Z naught has a large value. Okay, so you have a short transmission line and Z naught is high in value. High Z naught, I will remind you that in microstrip implies narrow width. We'll see this again later, but high Z naught implies narrow width. Okay, so now if you go and use the above, the argument is that if you have a short section of line, like here, and a large, relatively speaking, characteristic impedance, not 50 ohms, that's not large, but larger than 50 ohms, large enough, then you can consider that this section of a transmission line is equivalent to a series inductance like that. And the value of this inductance is given by this formula here. Is that not nice? In fact, so now we know that if we deal with short sections of lines, if we choose a high impedance, then practically we can use a high impedance, like narrow microstrip, short section of a microstrip, so narrow in width means high impedance, characteristic impedance, but short in length section of microstrip can be utilized to replace, in fact, to implement an inductance, an inductor. Now, what else? We look at case 3C, and now we go to the other end in terms of the spectrum of values of the characteristic impedance. And then what we find here is the following. If we assume now that our characteristic impedance is low, which means what? That if we have a microstrip, your W becomes wide, all right? Then in that case, you can assume that this small section of low characteristic impedance line is low characteristic impedance line, small values of characteristic impedance is equivalent to a shunt capacitor. And the value of this shunt capacitor is given by this. Also very important, all right? So high Z naught, a small section, short section of line is equivalent to an inductor. Low Z naught, short section of a transmission line is equivalent to a capacitor. Okay, so now how do we implement that? Let's start with a capacitor. In a microstrip line, the capacitance is, in fact, the capacitance between these two conductors, like this. That's what it is. So practically, this is the capacitance per unit length, for example. So in this microstrip line, if we take a small section of the line here, and for this small section, short rather, in length line, we make the width wider or wide enough, then practically what you see here, this small wide section of line can provide you practically with a capacitive effect. So you can assume that the equivalent circuit for a shunt capacitor in microstrip form, so if you have a shunt capacitor in microstrip form, it looks like this. Okay. And in fact, here underneath it, it's the value of C and how that relates to the admittance of this section of the line. All right, so Y naught prime is the admittance, characteristic admittance of this section of line, the white section. Okay, now let's go the opposite direction. And instead of going to create for a short part of the line, make it wider, now we make it narrower, like you see here. A narrow W, like a capital W that I'm showing here, implies a higher characteristic impedance, and that tells us that this small, short, rather, section of line, which has length L, is equivalent to a series inductor. And in fact, the value of the inductance is given by this. Okay, so now we found how to do a shunt capacitor and a series inductor in microstrip form by using small sections. Okay, now we have the opportunity also to look at some additional circuits. And it will be good to do that because that is going to give us enough to go then back and say, okay, now that we have found the multiple LC types of circuits, how are we going to realize them? Okay, that's what we have to do. So we found, so you remember, we found that a capacitor, a shunt capacitor, can be characterized or can be materialized by a wider, short section of a microstrip line. A series inductor can be materialized by a short section of a narrow microstrip line. These two are important. So now let's go and see what happens when we have a series LC and then a parallel LC, like a parallel combination of LC, and in shunt configuration. So we have a series in series configuration, so between A and A prime. And we have, and let's put this A and A prime here, and we have A below, shunt configuration of a parallel LC between A and A prime. Okay, now, without going into very extensive derivations, which are in the book, I will show you that here because the book has it later and it's very confusing. So at this point, you need to remember that if I have a series LC combination between points A and A prime, this is equivalent to placing a stub between points A and A prime, which is open circuited at the end, that has a length lambda naught over 4, and I should use a different L so we don't confuse it with an inductance. Let's use then L here and L, because we have also a capital L for the inductance. And so, see here, you can always get confused. So this is going to be L. And then we have these values for Z naught. So if, for example, you know your capital L, your C, of course, then you're going to know your resonant frequency for that, which is the square 1 over the square root of LC, then your Z naught of your equivalent open circuited stub that is placed between A and A prime is going to be equal to 4 omega naught times inductance divided by P, where omega naught is your the resonant frequency of this LC circuit, and the length is a quarter of a wavelength of this transmission line. Now, the series LC, it could be in a parallel configuration, so it could look, let me in fact add the page here. So this series LC could be either, first of all, so this is a series LC, so case 1 is where this series LC is connected in shunt configuration. Which means, what does that mean? It means that I have these two lines of my circuit, points A and A prime, and then I have my LC here. Okay, in that case then, your stub is going to look like this. A here, okay, A prime, and the stub is going to look like that. In this particular case, going to be open circuited. And here, open circuited. Z naught, and this is L. Okay, and that is a series LC in a shunt configuration. Now, you may have as case B a series LC in a series configuration. So, series LC in series configuration. What does that really mean? That means that if I have now a circuit that goes like that, that's going to be, well, probably not that good. That's going to be L, C, okay? And in fact, if I were to trim it here and here, and then make enough space and move it a little bit off this one. These are points A and A prime. Then practically my stub in this case is going to look like this. It's going to be I will draw it like that here. It's going to be a series configuration for a stub. Open here. And then here underneath it is going to be the rest of the line like that. This is going to be A prime, And this kind of like that, the transmission line. So we don't. And this transmission line is going to have Z naught and it's going to have length. Okay. And so that is going to be a series stub. Okay. And we said, depending on what type of transmission line, that may or may not be appropriate. So, but anyways, that's what it is. If we want to find a transmission line to represent that. Okay. Now we have another, which is the parallel LC in a shunt configuration. And that we find is equivalent now to a short-circuited section of line L, where now, again, omega naught is the design frequency, is the 1/square root of LC. Z naught is given by omega naught times L. Omega naught is 2 pi F naught, obviously. And the length L now is lambda naught over 4 plus an extension delta L, which is given by this function, C Z naught over 2 pi. So that's where we have. Okay. Now, let's think how we are going to use all of these to be able to materialize in microstrip the original circuit, which is this one. And let us in fact take this, because what I would like to do is to first of all show you how we are going to realize it, and then we are going to start trying to put the values in there. All right, so let's take this one here. First of all, copy it, and then go down where we're going to make the implementation. Okay, here, and then paste it, and that's our circuit. So now we have to materialize, to implement it in microstrip. So microstrip implementation in microstrip. Let me in fact increase. In microstrip. Okay, so that's what it is here. All right, so let's think about what we're gonna do. First of all, these two, this one here, and this one here are identical. And we are going to only worry about one of them, and then the other one is going to be the same. Okay, for this one, let's look at this. Is exactly what we see here. Okay. In fact, we found here a way to create that microstrip configuration for this part of the circuit. Now, question number one, what is the resonant frequency here? We have three different types of circuits. So do we have three resonant frequencies? No, because what we said is all of these circuits have the same resonant frequency, and that we controlled and we made it happen during our low pass to band pass transformation. So if you plug in the values, you will see that all of these combinations have the same resonant frequency. What that means is the resonant frequency for this circuit is equal to 1 over square root of L1 C1 is equal to 1 over square root of L2 C2. So we're good with that. We have only one resonant frequency, and it's the resonant frequency for the filter that we have been asked to design. Okay. What are we going to do first about this? As I said, we'll take this one, and then we're going to replace it with something like that. Now, This is a problem for microstrip, obviously. Why is it a problem for microstrip? Because it has a short circuit at the end. But for at least for this exercise, let's assume that, okay, if that's what we have to do, we're going to open a hole at the end, and then we'll manage that. Let us assume for a moment that we're going to do it. Okay, so we don't complicate things. Further, you will see that you can avoid that if you want. But for now, let's try to do it in that way. Okay, let's assume that we'll deal with this hole that we have to drill at the end of the stub, so we connect it to the ground. Okay, so as step number 1, we will replace this one by L1, C1, and how should I do that? Not really. Extend that like this. Okay, if we assume that these are these points here, A and A prime, that's going to be a stub with short circuit at the end. And then we have the characteristics of this stub. Say, let's call this Z01 for this one, and L, which is lambda naught over 4 plus delta L. And let's call that L1, okay? So this is what we are going to do for this part. So step 1 is practically to replace the L1C1 parallel in shunt with this circuit here. And in fact, let me change this color so you can see it better. Okay, this one. Then, what are we going to do about the L2C2? This is a series combination. And it's very, if it's difficult to drill a hole in the substrate and then put a VI in there, it's rather extremely, if not impossible, to do a series stub in a microstrip form. But we have something that can save us. And what really is going to save us? What is going to save us is this, that we can make a capacitor like this, and this one that we can make an inductor like this. All right, so now we're going to do the following. We are going to go back and I will draw for you a possible then arrangement. And with that, I think we're going to finish our class today because it's already close to 2:25 your time. But here is how we are going to, in fact, for step 2, let me write the step 2. Step 2, the series inductor, we are going to have for that a section of a line, a small section of a line, and it's going to have high impedance. So Z02, and that's going to be high, and that is going to be L2, and let's call it high just to remember it. And this one here, let's put this color. And then step 3 here is to replace the series capacitor by a section of line okay, that has a low value, low, and then has a length, L2. Let's put low here so we remember this. And then let's give it a different color. All right, so, oops, this one, so we can see how we're gonna put those together. Okay, so now we take those and we try to put them together and here how it looks. We are gonna have, in fact, to also make it symmetric, I would suggest that we would put the, you can write your circuit as follows. You can write your circuit like two inductors, one capacitor, another inductor. These two the same, so let's call them L2 divided by 2, C2. And then here you have L1, C1, and here you have L1 again and C1. Okay, so now we are going to take this and replace the different parts. And what we're going to do is, let's call that L1, C1. So the L1 parallel C1 is going to be a section of line. So let's do it in transmission lines. Here, we are going to have one section of line for this one inductor. Another section of line. In fact, here's like how we're going to show that. So we're going to have one section of line. We'll make it a little more narrow here. We're going to have another section of line for the capacitor. The same section of line for the inductor, the other part of the inductor. Then here we're going to have the stub. And then here we're going to the front lines, to the lines towards the generator. And this here is going to be the line towards this Z naught. This is going to be Z high to Z high to Z low to, and this is also another stub here. Short, and these two will be Z01, Z01. So practically what we have is the capacitor here, the capacitor is here, the inductors are here, and the stubs are here. And the others are the input lines. So now how this is going to look is the following. If you were to do it in Microstrip, as I will ask you to do as part of a homework, the microstrip is going to be a 50 ohm line microstrip here. Then you're going to have a stub. And at the end of the stub, you will have a hole somewhere. Okay, usually we show it like that. And then you're gonna have a narrow line for your inductor like this. In fact, you will have to do a little bit carefully. And that is gonna look like this. And then you're gonna have your capacitor, the other inductor, and then here you're gonna have your stub. Now, the lines, the way I have made them, are not necessarily accurately drawn, all right, obviously. There are a number of problems here. So, because this one needs to be symmetric. Okay, well, so this one, and this has to go closer. All right, and this one has to go here. And the stubs, obviously the lengths will have. So this is your microstrip. In fact, if I were to put this here, that's how I would do this filter. And this filter is gonna be my bandpass. Now, what I will do for Monday, and we'll probably just spend 5 minutes to go over, I will give you the exact values for the dimensions. And then I will ask you in the homework, I will give you for next week something similar to do. But this is how the filter looks like in microstrip form. Okay, so that's what I wanted to show you. In fact, I think that by now, we have covered really quite a bit. You can do all kinds of filters, even with these fundamentals. And not, everything that the book has. You will be, welcome to read additionally if you want from the book. But I think these are the very fundamental material that we need to understand, and we have covered enough in terms of filters. So with that, I just wanted to thank you, and now you can access your quiz, and then you will have until Monday, just the time we start the class, to finish it. So thank you very much. Goodbye. Okay, the majority, 40 out of 49, did the right selection. It's a voltage source, so it starts with a capacitor. All right, those six who did A, I suggest you guys go back to the textbook and see that it very specifically says in the beginning of the filter design with the insertion loss method that when your source is in the form of the Thevenin equivalent, so voltage source, it starts with the capacitor. If it's the current equivalent, it starts with an inductor. In 3 stages, if you start with a capacitor, you're going to have one capacitor, one inductor at the center, another capacitor at the end. Okay, so 2 capacitors, 1 inductor, as opposed to the opposite, which is in A. 2 students did all of the above, which is incorrect. You cannot have 3 capacitors only or 3 inductors and have a maximally flat filter. Yes.
I thought the Kuroda identities said you could transform an inductor to a capacitor.
Not if you have not for high pass.
I just thought it was in any case.
You cannot, unless you start incorporating transmission lines, you cannot do that. At least we have not seen it in what we have done. All right, I'm not talking about other sections of the book. I don't know. I'm not, we have not covered all the filters, but the material we have covered. I just wanted to show, to tell you that for the material we have covered, the equivalent source, like the equivalent, it's Thevenin or not Norton, will change the order of your elements. Is that, do I miss something? The Carotta transformations, yes, they can change an inductor to a capacitor, but they introduce sections of lines in there. So you have to have transmission lines also incorporated.
Dr. Chiktayi?
Yes.
Does the, whether you start with an inductor or capacitor, does that only depend on the source, or does that also depend on whether you're doing a maximum flat or equal ripple?
For the prototype, it depends on the source, and I will tell you why. Because it's the G values, all right, they give you a value for, the first one is always an impedance value, and then, so let me tell you, 1 second, I will do the following so we can talk about this better. So let me just do the following here. If you bear with me for a moment, I will get a book that I have in front of all of us and then discuss it. Okay, so here it is. I've been looking into it. All right, so this is our book. I have it electronically. Let me see. All right. All right. You see these two? We always, when we are in, this is what we are referring to. There are two important issues that you need to remember, because the values we get will specify of whether we have an inductance, conductance or a resistance, both at the source or at the load. And the source we always select, all right? So when the source is given like this, then we always start with a capacitor. This is the rules we are using now. Let me also say that I'm sure in design, you will see all kinds of different filters. They start with all kinds of different ways. And then people follow totally different types of designs. And if you go and then work in industry, you will see that industry has its own design tools for filters, which are very, very, very specific to the types of filters that industry wants to design. So, and you could probably see everything different, totally different from what we say. However, for this particular approach that we are using here, we need to follow what the process, because the tables we have available to us have been very specifically designed for those kinds of constraints. And the other constraint that is also important is this one that I have in front of you, that says that G naught is a generator resistance or conductance, obviously. Resistance in the Thevenin, conductance in the Nortons. But then there is another important one which you don't see in all filters, but only in the equal ripple. Look at the last element. The last element here, you don't see my what I'm doing unless I can, but I will not try to mess up right now. But the last element is the G at the end, is the G sub n plus 1. N is the number, indicates the number of stages. N plus 1 is the last element, you see. And very specifically here, it says the Gn plus 1, look at it, it's a load resistance. When Gn is a shunt capacitor, the last one is a capacitor, it's a load conductance if Gn is a series inductor. Now, you can say when I have ones as values of Gn plus 1, it does not matter, and I agree with you. Because if Gn plus 1 represents a load resistance and is 1, the inverse of this is going to still be 1. All right? So you can still call it a conductance or a resistance. However, if you go to maximally flat, look at the maximally flat at the last element. It changes. So if you go to stage 3 of maximal, of equal ripple, if you go to stage 3 for the 0.5 dB ripple, you see stage 3, two stages, last element. So G sub 3, but n equals 2. Look at n equals 2 and the last element. G sub 3 has the value of 1.9. But G sub 3 is going to be what? According to this here, according to this, G sub 3 is going to be a resistance if the last element is a capacitor. So the 1.9, you will have to multiply it by, when you do an impedance transformation, you will have to multiply it by 50, all right? And if it's a conductance, what do? You divide it by 50. So in the case where your last element, Gn plus 1, is a resistance and the value of Gn plus 1 is not 1, then if it were to be a conductance, it would have been a different value. Okay, so looking at this specifically for the equal ripple is very important to keep this in mind. All right, so that's what I wanted to show you. Any questions now on those before we continue today, or any other comments? Okay, I will assign it as a review so you can see it. So now we are going to continue with filters, specifically with the realization. We started to do it with Karoda transformations, all right? So we started last time, and please stop me if you have any questions about this. Last time, we decided to do Karoda transformation on a simple filter that has only 2 stages, one capacitor and one inductor. And these are the values. It was a maximally flat, and it satisfies everything that you see here in the box. And then what we do is that we applied, if we were to develop a low-pass filter, all right, a low-pass filter would need to go from the G values, obviously, to a realizable filter. So we have to apply 2 transformations. And the 2 transformations are here, impedance and frequency transformation, to make it a low pass. And indeed, when you apply these 2 transformations, you create this low pass filter. Okay, so now we have that filter. And now we say, we don't necessarily want a low pass filter. Somebody comes and tells you, now do a similar kind of a filter, but I want it to be, what did I say, band pass. And they give you a particular delta. Well, you know, they give you they don't give you a particular delta, but they will give you a particular frequency and they will give you a particular bandwidth. And then for that, we saw in the past that you were able to apply these transformations. All right, you remember those transformations where we changed each of the element into a combination of L and C. And we stopped there. Okay, so now we said, okay, we created a bandpass filter. You could do it, you could do exactly the same to this filter here. For this filter to be a bandpass, you would have to change C by an LC in parallel and L by an LC in series. So instead of 2 elements here, you would go to 4. All right, we saw that. Now we go back and say, okay, now let's try to do something different. We still want to stick with the low pass, but now for the low pass, I want you to materialize it using microstrip, using transmission lines. I don't want you to create a capacitor and an inductor with whatever frequency, you know, like lumped elements. Somebody's going to tell you. We just don't have the particulars to do it. It might be that you are in low frequency, so your inductor will have to be a coil. How are you going to do coils? You know, in 1 gigahertz, you may have, the capacitor is going to have, if you materialize it with transmission lines, you may have a lot of parasitics. So they come and tell you, I mean, with microstrip, I mean, alone, do what I meant to realize the inductor is a spiral inductor, the way we saw them. You remember we saw a lot of parasitics in the spiral, and that spiral inductor, it was in a CMOS substrate where everything is very small. Could you imagine now a spiral inductor with large inductance value on a regular microstrip? It's going to be a huge inductor. And so the whole circuit is going to be dominated by the inductor. And not only that, it's going to have a lot of parasitic capacitance. So then people say, okay, I don't want passives in lumped form because the parasitics are so high and they're not going to perform well over a large bandwidth. Okay, then they tell you, you decide to go and use transmission lines. That means that we will have to replace L and C with transmission line elements that have the same kind of performance. But we just don't do it simply like that. There are a number of transformations that you have seen in the book, and those transformations are here for you. And for these transformations, you can see, look on the left. Practically, in this transformation, this particular one, you have a shunt capacitor here. And you would like to change this capacitor into an inductor for whatever reason. So you will have to match, to bring this capacitor next to a transmission line, to find a transmission line. And then from there, you can replace this combination of shunt capacitor with a Z0, with Z1, which is transmission line, to another transmission line on the left and an equivalent inductor on the right. So practically by doing that, if you have a section of transmission line next to your element, then indeed, like your colleague said earlier, you can change one capacitor to an inductor, or you can change an inductor to a capacitor. This is very useful, obviously. And the first ones are the ones we have seen in low pass filters, all right, a shunt C and a series L. But the other two also help if we have a shunt L. And then in this particular case, it gets a little more complex because then we are including transformers. And we have not talked about this. How do you do a transformer in microstrip? but very briefly, I will tell you at the end of this chapter how to do that. So we are going to stay away from the last two, and we are going to work with the first two. So we are going to, for now, stay away from this. And we are going to focus here on these two. And as a matter of fact, as an example, in our case, we are going to practically work on the second. Okay, so now keep that in mind. We go back to our problem. All right, you need to keep in mind how you change an inductor to a capacitor. And how do Z1, what is Z1? If you have an inductor, what will Z1 be? Can somebody tell me? What is the equivalence impedance to an inductor? If I knew the inductor value, what will be the equivalence impedance?
J omega L.
Yes, and without the J, I would say, because you will see we don't use the J in this, it's going to be omega. I will put the J here, but I will put omega L1. And which omega is that? Obviously, since we do it at one frequency, for a low pass, it's going to be the cutoff frequency. For a band pass, we're going to work at the center frequency, at the design frequency. All right, for a low pass, our design frequency is the cutoff. That's where we set all of the dimensions and the whole thing. And of course, we operated below that for a low pass or a high pass above this, but omega sub c is our design frequency. But for a band pass, is the center frequency. And around it, we have the bandwidth for a band pass. Okay, so it's this. What is going to be Z2 then? So Z1 here is without the J, just because of, you will see the formulas, all right? You see that you have Z2 over Z1, and then square is a real number here. So Z1 is without the J. And how much will be Z2 above in the capacitor case? How much is Z2 here?
Omega C.
Exactly, omega C, omega sub C, C. Okay? So in this one, you need to remember, let me now erase this part, that your n square, let's take it in our case, all right? In our case, we're down here. Our n square is 1 plus Z2. Z2 is the transmission line characteristic impedance. So, and this is Z naught. I will call that Z naught. Over Z1, which is omega sub C L1. Okay, let me rewrite it a little bit more. It does not look good. So n squared here is 1 plus Z naught over omega sub C L1. So if you have a section of a line, and it says here, all sections of lines are how long? Lambda sub C over 8, the ones that you add. That's why these formulas have been developed with the assumption that this transmission line is lambda sub C over 8, okay? All right, so then you translate it to this one where now this is lambda sub C over 8. And that is the other transmission line. Let me call that like this on the second side. And then here you have a capacitance, all right? And omega sub C, C is, according to that, n squared Z2, all right? You see those? How do I write those expressions? Do you see that?
Yes.
Okay, now we will take this and go down to our case. So our case has a shunt C series S, series L. What do I need to do? And I have two transmission lines, one on the left, one on the right. And you see that I have made them extend it without any specific length. That means that I have enough line there. I can extend the line as much as I wish around this filter. So what do? I take one part of this line, which is lambda C over 8. I take it like this. And then I leave the rest of the line, which is also Z naught. Okay? You see that? I have not changed anything because these two sections both have Z naught, and therefore I see here the same impedance, which is Z naught, as I see here. So adding a section of a line has not really changed my filter performance, none. Do you agree with that, or you want me to explain more? Okay, I don't hear any questions. Now I will take this one and this one I will keep it here. I will call it Z2. So it's this one here. It's this one. That I call it Z2 is nothing else but my lambda C over 8 transmission line. Lambda C, over 8, exactly. That is Z2. And then I apply the formulas that I showed you previously, and I explain here what I have. I have practically what I did, I changed the length of the transmission line, and instead of this one here, now what do I have? Let me add one page. What I have here, so I went from this one and that was connected to 1/8 of a line. I went from this to this one, where I go now to a new line, still 1/8 at the cutoff frequency. Has a different impedance. If I call this Z1, this is going to be Z02, just to remember. And this one has a capacitance, C. A new capacitance. Let's call that C2. And these are given by the following relationships. So n squared of Z01, it's equal to Z02. And my capacitance C2 omega, say sub C, C2 equals n squared Z2. Rather than, I'm sorry, wrong in this one. It should be this one. And how do I see the wrong? You cannot equate, so I will have to correct this one if I did anything. Let me see. Yes, I should have seen this here. I cannot do this. This is so wrong. I cannot do this. Why is that? Because I have an impedance here. It's an impedance. You cannot make that equal to omega sub C. So practically the way it shows there, if I read it carefully, is going to be the following. We'll correct it here. It's going to be omega sub C equals 1 over n squared Z2. That's the correct, okay? And then we're going to put this here. And I found it because you cannot make Z2 even if they're simple numbers, equal to an omega c. So it's going to be practically 1 over omega sub c c2 equal to that. All right, so we got that. How much is n squared? N squared equals 1 plus, what did I say, z2 over z1. If I remember well, don't remember all of this by heart. Let me see. Is z1 over z2 over z1, correct? N squared. So practically, I'm going here, and I will have to find that ratio. For our case, this ratio is equal, how much is z2? You remember? Z2 is 50 ohms, Z naught, and Z1 is omega sub C L. So if I put here, this is 1 plus omega, let me see again, Z2, which is Z naught divided by omega sub C L. And that's the value of n squared. And for our case, for our values, this value of n squared came out to be 3.36. Okay. So, there is one more thing here. So now what we've done, before I go down here, what I have done is the following. I have changed my inductor to capacitor. And now what I have here is, to show it better, I have an incoming transmission line, which I had from the beginning to my filter, which is 50 ohms. Then I have the first capacitor, C1. Then I have another section of a transmission line with different characteristic impedance now, all right, which however is L sub C over 8. And then I have another capacitor, C2. And then I have another section of a transmission line, which is the output transmission line. All right, so that's practically what I have. That's what I've done. Why was that important? First of all, if I were to replace both my capacitor and the inductor with stubs, the capacitor with the shunt and the inductor with the series, I would have two problems. One, that it would be difficult to do a series stub for a microstrip. Two, that I cannot have one stub next to the other. I mean, it's very difficult for a layout to do that. Okay, so now I was able to change. As you can see here, both, in fact, up here, because here we got our original circuit to this one. Any questions so far before I go to the next?
Is having two stubs next to each other just like a physical limitation? Just like there's not a
Yes,
space?
there are all
Okay.
kinds of layout problems when you do that. If, for example, you put them one across from each other, so let's assume, all right, let's assume that you want to put two stubs on a microstrip. Let me do it this way. I will put one stub. I want it, let's assume let's assume that I have to put a shunt stub here. And this looks like this, and it's normally short. All right. I mean, we try to make them small, as short as possible for conductor losses. And then you want to put another one next to it. First of all, if it's series stub, you cannot put it, all right, in microstrip. But if let's assume it was a shunt stub. And how would you put it? You cannot put it on the same side because it would be just a thicker stub, all right? So you cannot do something like this and then, oops. You cannot do in microstrip. I mean, give me more space. You cannot do in microstrip something like this. Why? Because there is so much coupling between these two that they behave like one if they're too close. And for them to not be coupled, they have to be farther away. And if they are farther away, then you have a section of a line that is going to change your circuit. So if you put them like this, then this section of the line is going to introduce its own impact, and it's not going to be controlled because, you know, then you do it arbitrarily. So you cannot do this thing here, and you cannot do that without specific design of the length, and that's what we do here. The other thing you cannot do in a microstrip is to do something like that, because that by itself, if the length is that length is close to half a wavelength, then, or even close to 1/3 or 1/4 of the wavelength, then this is going to radiate like an antenna, like a dipole. And so you're going to have a lot of losses from here. Usually radiates like this. So you do it only if you have very short stubs. So the total here is very short in some cases. But I would say for now, for you, try to stay away from stacking stubs one on top of the other. Okay? All right, so now we are going, what are we gonna do? Be very specific on how we replace stubs and what we replace them with. So here, what Carota transformations are telling you is that you replace stubs, you replace capacitive elements by stubs. And if your stub has a length of lambda c/8, then practically what you see as an input impedance is nothing else. Let me in fact use a different one, use yellow. I'll use a different to see it. Look at this one. So if you use a stub which is 1/8 of the wavelength, then your input impedance, whatever the reactance rather, that you see in this stub is equivalent to the characteristic impedance of the line that makes this stub. So practically that's an easy rule. 1/8 of a line at that design frequency is going to give you a reactance whose value, exclude the J, is going to be equal to the characteristic impedance of the line. So practically, I can immediately design, like shows here, to replace a capacitor, I can design an 1/8 of a wavelength of a shunt stub that is open at the end. For a series, it has to be short. For if it's series, short gives you J times the characteristic impedance of the line as an input reactance of a shunt, and open lambda c/8 will give you an susceptance there, which is like equal J included to the characteristic admittance of the line. Okay, so practically now what we have done with this, and I will skip the steps because we talked about that, is to create this one here. And I will leave you with the following thought. If you apply exactly the transformations, and this is 3.3 here, all right? It's not 33. Let me clean this up. Okay, if you apply the transformations, you see something that is already problematic. First of all, this is 500 ohms. The characteristic impedance of this red ZOS, it has to be 500 ohms. This is huge. The other one is very low, but it's okay. 31 ohms is not that bad compared to 50. But if you have a line like this, a microstrip line, this thick, on one substrate, for example, and looks like that, and it's 50 ohms, then a line that is going to be 500 ohms on the same substrate is going to be very narrow to give you that kind of characteristic impedance. Why is that? Why is it going to be so narrow? Because Z naught is the square root of L over C. All right, same thing here. Z naught square root of L over C. The wider the microstrip, the higher the capacitance. Or the more narrow the microstrip, like this, like a dot practically, the lower the capacitance, which gives a higher impedance. But what happens when you have two narrow lines? That the conductor loss is going to be very high. So very narrow microstrip lines increase here the conductor loss. So very narrow lines are out of the question. Not appropriate. So what we're going to do next time, we're going to see how to change this, how to avoid this problem. These are all very important and will help you in your project, because today, I'll give you 2 weeks. Today, for the next project, I will ask you to use whatever you see from here, to use Microstrip to create the filters that you need for your project. Whatever filters. Now you have the capability. Do the simple, don't go out of your way to do extreme things. That's what I would like to suggest you. Even if you are to use MATLAB or something else, try to be as simple as possible. The simplest solutions are the best solutions. You need to keep that in mind. So these important considerations, I will continue with this next time, especially for Microstrip, are important when you start deciding how to deal with these dimensions. Now you need to remember these are design problems. In design problems, there is not only one solution. This is mathematically a correct solution. But if you were to make it and try to implement it, a filter like that will have higher losses from another filter that will have better characteristic impedances. 210 is already high, but not unacceptable. 500 is way out. So we'll talk about this next time. Any questions? All right. Thank you so much. I will we'll stay here at 3 for office hours. Join me if you want. Thank you.